Hello, everyone. My name is Amy. I am a recent graduate from St. Olaf College, and I would like to welcome you to the Cryosphere Pavilion. We have an event right now on A Tale of Two Oceans. I also want to welcome everyone who's watching virtually from our two hubs in Geneva and Stockholm. If you have any questions, feel free to speak up at the end, and we'll have a microphone over to the right. And if you're listening virtually, feel free to put your questions into the chat. I would now like to turn it over to Libby Jewett, who will be moderating the session.
Yep. Thank you. Thanks for coming today. My name is Libby Jewett, and I am from the National Oceanic and Atmospheric Administration. I'm in charge of the ocean acidification program there. And today we have a great lineup of speakers. The title is The Tale of Two Oceans, sharing the latest innovative approaches and evidence-based research from food webs to feedbacks to raise ambition towards a sustainable future. So the flow of the panel today will be first to have a more general overview of the issues, which Dr. Richard Bellaby will be giving, and then more detailed examples of how these issues are affecting polar oceans. We will then hear about new technologies for looking at science, at tracking changes in chemistry and looking at science and solutions moving forward, before ending with our final speaker, bringing it back together to discuss multiple stressor landscape and that relationship to policy. So I will introduce each speaker before they speak, and almost everyone is here except we have one remote speaker. So our first speaker is Dr. Richard Bellaby, who is lead researcher at the Norwegian Institute for Water Research and also director of the Center for Marine and Coastal Research at East China Normal University. He researches the interplay between climate and ocean change, marine ecosystems, and ecosystem services, including socioecology. So Richard.
Okay. Thank you again for the opportunity to speak in the Cryosphere Pavilion, the second of three. I have been invited in the 8 minutes, which I've been encouraged to stick to introduce some of the science behind, for those who have the opportunity to be here, these pillars of information and latest findings, which you can also pick up physically behind here. It's the State of the Cryosphere report for 2021, a needed decade for urgent action. You can also find this and download it on the icci.org, I think, website. So you can, very powerful statements in here, and I've stolen a few. I think on the first page, we cannot negotiate with the melting point of ice. That's a very powerful statement about our fragility, or the fragility of the polar oceans, but also the sensitivity and the importance of keeping to low carbon CO2 or carbon emissions. And this is argued for many of the different states, as in ice, ocean, permafrost, in this report. I'm slightly biased, and I'm sure Libby will support me. There's also a lot of carbonic acid being formed in the poles. You heard this morning. Well, sorry, we're not allowed to refer to other talks, are we? Because we don't expect everybody to be there. Both the Southern Ocean and the Arctic are undergoing the largest changes in ocean acidification, and that will be included in my overview. So for those that have a busy timescale and can only be here for the first three slides, first of all, I'd like to define the cryosphere. This is the Earth's snow and ice regions ranging from ice sheets, glaciers, and permafrost to the sea ice, and it also includes the polar oceans, not just the ice in the oceans, but the polar oceans. again, from this report, cryosphere changes, if allowed to continue, will be permanent and the most on all human timescales. You'll be quite shocked when you hear some of the timescales that is in this report. Many and possibly most of the processes that I'll be talking about will be permanent changes under the 2-degree goal, but could, and this is the opportunity, we show how you can hopefully avoid or reduce the impact of these massive changes if we remain close to the 1.5 degree. And the connectivity of the Arctic, both through the processes that occur in the Arctic influencing atmospheric exchange and also water energy exchange with the rest of the world, that the impacts are happening in the Arctic will damage human communities on a global and also an overwhelming scale. So the first one, and this is Mike Meredith's chapter in the IPCC SROC report from 2019. The trends in the Arctic and in the southern, certainly in the Arctic, are the highest in the world of surface warming. It's a little bit mixed at the moment, and it's very regional in the Southern Ocean presently. However, from the IPCC policy document, which is available and quotable as opposed to the science document, which I'm not allowed to tell you anything about. You can read it on the net, but I'm not allowed to say anything about it. You see that also in the future, the Southern Ocean also has a very high sensitivity to increasing CO2 and climate change. And they say it is virtually certain, and this is a very strong term in IPCC talk, that the Arctic will continue to warm more than the global surface temperature with high confidence over 2 times the rate of global warming. So this is big changes ahead. This is transferred into the ocean. I'll start with the lower figure first. We read and we hear so many reports now of massive warming trends observed from time series but if you look at 2020, we're not too far above just above the mean for the historical variability. Very soon we are going to go very quickly out of this present discomfort zone, because we're already worried about it, but we're going to go way out of it now. And very important as well is the top figure when we're relating to the ecosystem, the ecological presentations that are later, is the heat waves that we're reading about devastating many systems are also going to increase. Even under the low scenarios, there will be a 2 to 3 they'll happen 2 to 3 times faster, more than they are doing presently today. I have to assume in this short time that you are aware what ocean acidification is. I use this, and this was developed to represent Arctic ocean acidification and why it's more sensitive. Well, first of all, it's sensitive because it inherently has a lower carbonate ion concentration and therefore is more sensitive to per unit uptake. So for one uptake of carbon unit, for 1 unit carbon uptake, you will get a bigger pH change in the Arctic and in large parts of the Southern Ocean in pH or aragonite saturation state. But it's also very sensitive to permafrost changes. It's very sensitive to precipitation changes, freshening the surface ocean. And it's also very connected with the Pacific and the Atlantic. But I've added, just for this talk, and soon the Southern Ocean, because there will be significant parts of Antarctica soon which will have a ice-free coast with rivers. So we have to start thinking of the Antarctic coast in a slightly different way than the ones that we do now. But again, I can't go into the detail in the short time that we have here. What is more important is to highlight the sensitivity of the polar regions. Under a low emission scenario, 2.6, we will already see large areas of the Arctic, mainly on the on the Russian shelves. But if we carry on business as usual, and even over if we hold to the 2-degree target, there will be massive areas in the Southern Ocean and in the Arctic, and also in the North Pacific and parts of European seas, which will have what we try. A Aragonite saturation state is very hard to explain. We say this water will be corrosive. It'll be corrosive to calcium carbonate, which doesn't have strong protection, biological protection. That's about all I can say at the moment. If you're more interested in that, straight after this session, there will be a focused talk on acidification. But this is what is alarming. I mean, the science behind it is quite old. In fact, it even goes much further back to Dave Archer's work and Andy Ridgwell's work, but for the scientists here. But the small perturbations that we make, even now, even if we hold to 1.5 degree, they will go on for 10 to 100,000 years. And with a 2-degree scenario, between 50 and 70,000 years. And actually, we'll reach one critical threshold in 14 years' time, according to this work. So I've been told to hurry up. So I'm not an ice scientist. There are some excellent ice scientists present here. It's quite guaranteed that even at 1.5 degrees centigrade, there will be ice-free Septembers. If we go to 2 degrees, these will be lengthening to several months. We will still get ice formation in the winter. It will still be dark. It will still be cold. However, this ice here is only 1 year old. There is no multi-year ice, which is supporting important ecosystems. What we have to also consider is that I've talked about all these stresses or these changes individually, but they're all happening at the same time. They're all contributing, and a particular ecosystem or a particular organism will respond differently to and also different regions have different and different local levels have different combinations and different concentrations or different extremes of these stresses. So I think Carol will be happy. I've been told I have to stop, but if you read The State of the Cryosphere, you can see that we can stop these changes. But for example, some are very important things that even if we stop the permafrost emissions will continue for many hundreds of years, even if we stop CO2 emissions now. So there's still an awful lot of inertia in the system. Ocean acidification and permafrost loss are the two biggest long-lived processes which we've highlighted in this report. But I shall leave it on to the next. Thank you.
Thank you, Richard. And all of you stay tuned because he will be presenting in the next session as well. So next we have Dr. Angus Atkinson, who is a researcher at Plymouth Marine Lab here in the UK. He is interested in all aspects of marine ecology and biogeochemistry with a primary focus on plankton and krill species in polar regions. Take it away.
I'll move the microphone up a little bit. Richard gave us a really nice introduction to the environmental change in the Arctic and the Antarctic. I'm going to give 8 minutes or 9 minutes talk on some of the responses to the animals and plants, and a so-called universal response to climatic warming is a poleward shift in the geographical range. So as isotherms move towards the poles, the animals tend to keep their thermal niche and move polewards with them. So I'm going to be using Antarctic krill as a case example of that. So why study Antarctic krill? There's a lot of reasons. Two of the really obvious ones is their enormous biomass, and also their key role in the unique and iconic food web of Antarctica. And I've just shown in this schematic just some of the predators which are wholly or partially reliant on krill. Two other reasons: they support an enormous fishery. It's extracting at the moment about 1/3 of a million tons of krill a year, and it's expanding. And also major biogeochemical agents in the transfer of carbon. And I've just got one slide to illustrate that carbon issue. They've got a circumpolar distribution, as I said, an enormous biomass. It's concentrated in this Southwest Atlantic sector. That's a heat map showing the high biomass in the Southwest Atlantic sector. And in that sector, they're one of the major grazers. So they're efficiently repackaging primary production fixed by photosynthesis, repackaging that carbon. Their poo is relatively large, sinks rapidly. So it's a relatively efficient way of exporting carbon from the surface layers of the ocean. I'm going to be talking about range shifts. And I've put this slide up to show that it's absolutely not a given that species shift their range towards the poles. We've had huge amounts of speculation that this is a response of animals in subarctic and Antarctic environments or polar environments. Huge amounts of speculation, modeling, sort of climatic envelope modeling, but there's actually very, very sparse data that this is actually happening. There's admittedly more coming out from the Arctic, but certainly from the Antarctic, there's a lot of impediments to range shifts. At both poles, the isotherms are converging, so there's less living space, shorter growing season, but there's also physical barriers. There's in Antarctica, there's the Ekman drift on the currents, on the circumpolar current, that they have to fight against. There's also physical boundaries with the ice and bathymetry and the landmass itself. So in the Southwest Atlantic sector, we've got a particularly large population centre of krill. It's also well served with data. We've compiled this data from the last century into a database called KrillBase. This is just the last 40 years of the data where it's particularly dense. So we've got two sampling eras that we've divided this last 40 years in, 76 to 95 and since 95. And we can see that the heat map is showing a very large population in the Scotia Sea in the early part, and that population has declined and it's contracted towards the Antarctic continent. So this is against the surface currents. So that's it looks a little bit sort of abstract, seeing sort of color-coded grid squares. So I put it into a human equivalent. So this left-hand map, the area of that map has a population biomass of krill that is equivalent to the human population of USA and China combined. And in that, in the period between these two sampling eras, if you can imagine that population halving and moving over 1,000 kilometers polewards. So that's a massive relocation that if it was happening on land, we'd stand up and take notice. And that's why we're so interested in studying it and understanding what's caused it and understanding or projecting what's going to happen maybe in the next 20 years. So to look at what's actually been behind it, we've focused in on this Scotia Sea area, and this is a sea surface temperature trend. And Richard was saying ongoing trends. This we've seen a rapid increase in temperatures in the first decades or the middle decades of last century, but then there's been a little bit of a hiatus. That's actually quite important to what I'm going to say next. So to compare this temperature trend with the krill population movement, we've chunked it into 5 time sampling points, 5 eras. So that's the green points. I've transferred them over to the left-hand plot. So we've got the temperature trend, rapid warming in the middle part of last century, then a leveling off. We've also got an independent data set on sea ice from last century. So you can see the open water period, or the ice-free season, has followed that trend as of the temperature. So if you compare that now with the distribution of the population centres of both the larval and the post-larval krill, the adult krill, it's a really, really surprising result, because when the water was warming, they've actually stayed put. They've maintained a consistent distribution in the Scotia Sea area. And it's only during this hiatus, the pause in the warming, that the population have shifted, and they've really, really shifted fast. 1,000 kilometres in only a few decades. That's a massive population displacement. So we wanted to work out what was causing this, because they're basically moving in a totally out of step way with the climate. So what we think is happening, it's actually a population dynamics effect. So we've got a population, this is the larval, the previous data I've showed was the adults. We've got larval data as well, and that's providing insights into the population dynamics. So in this northern sector, the main spawning area of krill last century, there's been a massive decline in the recruitment of the young krill to the population, and that seems to be affected by a climate mode called the southern annular mode. So that has got increasingly unfavourable. The low pressure systems have moved closer to the spawning areas around the tip of the Antarctic Peninsula, and that's probably provided a shortage of food, probably deep mixing, and that's killed off the spawning in that northern area. Concurrently, there's been a sudden increase in spawning down the peninsula, and this happened literally over a couple of years at the turn of the century. From about 2000, 2001, they suddenly started spawning in this southern area, and that was actually right in the middle of this hiatus in the warming. So to put that into a sort of schematic sense, we've got a distribution that has suddenly contracted due to a movement or a change in the spawning area, and now the distribution this century has contracted towards Antarctica, but that is in a totally different living space. It's a much more shelf-orientated distribution, and it's marooned some of the krill-dependent predators, for example at South Georgia, in the top right-hand corner of this schematic. They're krill-dependent predators, and their food has moved away from them. So it's got fundamental issues for life cycle completion, management, biogeochemistry, and so on. Just to sum up, there's been as I said in the sort of range shift schematic, there's been intense interest in projecting range shifts, and there's been a lot of modeling which is based on this fundamental assumption that species keep their thermal niche and they shift polewards with the isotherms. This is absolutely not happening with krill, so we've got to be incredibly careful how we project the future for krill. And often people talk about tipping points, but we have seen a very, very rapid change in where krill are spawning. So, for example, this morning's talk, there was a lot of talk about designing protection for krill and for ecosystems, marine protected areas. We have got to make these protected areas not just where krill and the other members of the ecosystem were, but also accounting for climate change and these sudden shifts. So I'll wind up there. I've heard the 1 minute notice. Thank you.
Thank you, Angus. I know I learned a lot, but I'm going to have some questions at the end. So next we have Dr. Henry Burgess, who's the head of the National, was that us? No. Natural Environmental Research Council. Is it national or natural? Okay. Arctic office. The office supports UK-based researchers in High North Research, provides advice to policy and decision makers, and supports new international Arctic science initiatives. So I'm going to turn it over to you.
Great, thank you very much, and thank you for the PhD. I'm afraid I don't have one, but I'll take it. That's fine. Thank you very much. So I'm Henry. I'm in charge of the UK's Arctic office. We're based at the British Antarctic Survey in Cambridge. Our job is to support the whole of UK Arctic research. And I'd like to do 3 quick things for you this afternoon. I'd like to tell you about this program, the Changing Arctic Ocean program. I'd like to tell you a little bit about part of the science that's come out of this program. I'm not a scientist, so I won't be showing you graphs, but I'll talk to you about some of the science that's coming out. And then with a final couple of slides, make an analogy, make some connections between some of the changes we're seeing and the timescales that we're going through, or that the changes are going through, and an iconic species. So as we know, the Arctic Ocean, oceans as a whole, are taking kind of the body blows of the increasing warmth, the increasing global warmth. The oceans are receiving, I think it's 91% of the excess accumulation of heat. And so there was a huge focus on what's happening in the oceans, particularly the Arctic Ocean. And we agreed 5 years or so ago, a new program between the UK and Germany to look at the biogeochemistry of the changing Arctic Ocean. To get a better understanding about how the ecosystem works from bottom to top, and to think about how sensitive those systems are to strains and stresses, and then to help inform the models for what's going to happen in the future. And it was a genuinely big program, £20 million over 5 years, from both the UK and Germany. The first time we'd done this together in this form. 32 research institutions, over 200 investigators, and many, many different partners across the world. And what was particularly important about this program was the science itself, and there have been 100 publications that have come from this program, and many more to come as well. But what was especially welcome was how much we could leverage support from other countries through this program. So the little kind of bars you can see here in pink are the cruises that were funded by the program itself on British research vessels and others, but the bars in blue are the cruises that we're able to use other countries' kind of assets for as a barter and an exchange program. And many of the findings from those 100 peer-reviewed publications that have come out are because of this international cooperation, and that's something that we cherish hugely in the UK, and we want to see even more of, tackling these big questions. So one of the things that I want to focus on is this issue of Atlantification, which many of you will know much more about than I will. But there were a number of projects within the Changing Arctic Ocean program that concentrated or had relation to this issue. These 2 of the 4 big ones, but also these programs as well. There were 16 projects in total. And so the work I want to talk about is work that was led by Dr. Jung Jern Len from Bangor University. And she was thinking in particular about how heat is transferred into the Arctic. One of the things that she said very powerfully in a session earlier on this week was that many people know that the Arctic as a whole is greening, and that's particularly true of the Arctic Ocean as well. The Arctic Ocean is greening, but understanding how that process is happening, how the heat is translating, how that warm, salty Atlantic water is coming into the Arctic from the Pacific and the Atlantic is something that they want to understand more about, and they've been investigating through this program. So she showed earlier on an animation that was developed with Scripps in the US. So I'll take the liberty of showing that now, which talks about some of these issues that we're thinking about. So as we know, the warm water is moving into the Arctic, and then it dives beneath the fresh surface layer. And this is about kind of that sense of primary production that's happening in the Arctic, that thin layer at the top, and how the warm, salty water, how those nutrients translate up to that thin layer and drive primary production, and in turn affect the sea ice. So one of the things they were looking at was how that process happens, and particularly what the connections are with this ocean mixing and nutrient fluxes. And they identified internal waves in that warm water as it's moving into the Arctic. And they identified that this is persisting for quite a long time, and it's affecting the the timescale of the algal blooms, the timescale of that greening in the Arctic Ocean. So that sense of this being this thin layer at the top of the Arctic Ocean, and once those nutrients are used up, then that's your bloom finished. But actually, if there's more warm, salty water coming in, bringing nutrients, mixing effectively with potentially stormier weather and reduced sea ice cover, then that's driving nutrients up to the top layer. And they identified that there were increasing amounts of bloom later in the mid and late season. And that will have an effect on the species in the Arctic, and it will have effect on the sea ice and other processes. So this is work led by Dr. Jung-Yeon Len in Bangor. The other thing I wanted to talk about, kind of finally in my session, was about some of the other products that have come out of the Changing Arctic Ocean program, and there's been a big focus on data to improve the models that we have. When you improve the models, you improve your ability to predict and adapt potentially, hopefully, to the future. And so this is some of the findings that have come out from the EcoLight project, particularly looking at the models of light through sea ice and in ice algal growth. And of course, that translates to other findings. This was shown by Neil Banas earlier on this week, the zooplankton ecology along current pathways. So you've got sort of the Atlantic water on the left-hand side there, and the Pacific water and the Pacific species coming in from the other side. And this is kind of tracking work that was done through the Diapod and Arctic Prize projects. And of course, this all translates through to kind of the higher levels of the ecosystem, and thinking what's happening to the Atlantic copepods down the eastern side of Greenland, and then the Arctic copepods, and particularly the connection to iconic species such as bowhead whales. This is a chart that you'll have seen lots earlier on, and other colleagues have shown it just in this session. Neil Banas, who I'm crediting for this, who showed this earlier on, relates this work specifically to bowhead whales, which the internet assures me these are examples of bowhead whales. And he overlaid the lifespan of a bowhead whale, which is around 200 years, to this chart. And you can see that the lifespan of a bowhead whale, 200 years, dates from our historical knowledge about change in Arctic sea ice, right through to beyond where we can confidently predict. He made the point, which I think is a very powerful one, that when we're thinking about change in the Arctic, of course, we're thinking at the microscopic level, the copepod, the plankton level, those very rapidly turning over life scales. But we're also thinking about the bowhead whale. And if you had a mother bowhead whale and a daughter bowhead whale, you can potentially cross the whole period from the start of commercial whaling in the Arctic right through to the uttermost end of the projections that we're able to make. And that's 2 lifetimes of one iconic species. And we think about these changes in our own lives, as we should, because then that will make us make changes. But when you think about it in a bowhead whale term, that's 2 lifetimes from when they were left alone completely to who knows what will happen in 2140 and beyond. And he made the point very strongly that what is science fiction for us in 2140, terrifying science fiction, but still at this stage science fiction, is essentially retirement planning for today's bowhead whales. And I think that's a light-hearted but also serious point to end on. So I will more or less finish it there, just to say that if you're interested in the proper science that came out of this, rather than my summary, what you will hopefully be interested in is our science conference on the 30th of November. And that's where all the projects, all those 16 projects that were funded through this UK-German collaboration, will be presenting their findings, very short, manageable presentations on the 30th of November. It's all online, so you don't have to be there in person. And then we'll have a policy event where folk from London and beyond are coming to hear some of the implications for them as a result of these changes. And that will also be available online. So thank you to PML for the opportunity, and thank you for being here. Thank you.
Thank you very much, Henry Burgess. And I did not know that bowhead whales live for 200 years. That's pretty powerful. Next, we have Dr. Helen Finley, who is a biological oceanographer at Plymouth Marine Lab here in the UK. She uses a combination of experimental, observational, and modeling tools to investigate impacts of climate change and OA on marine life, with a special focus on the Arctic. She is co-chair of the Northeast Atlantic Hub of the Global Ocean Acidification Observing Network, which you can hear more about in the next session.
Thank you, Libby, and thank you for giving me the opportunity to come and talk to you today. I'm going to be talking about ocean acidification primarily, so we heard a little bit about it from Richard, but hopefully I can give you a bit more detail. I'm going to talk a little bit about some of the knowledge gaps and how we're looking to new technologies to find some of the solutions and fill those knowledge gaps, and where we can go for solutions for thinking about mitigating change in terms of ocean acidification. So just to make sure we're all on the same page, I've got a little bit more time to go into detail than Richard had. The oceans naturally take up carbon dioxide from the atmosphere that reacts with the water to become part of the marine carbonate chemistry. And in doing so, it's actually managed to absorb about 30% of the anthropogenic emissions that have gone into the atmosphere since the pre-industrial times. But however, if we add too much too quickly, which is what we are doing, then we result in a change in that marine carbonate chemistry. It's an imbalance. It upsets the system. And that causes the oceans to become more acidic. We see a lowering of pH and also a lowering, importantly, of this carbonate ion concentration, which Richard was talking about, which essentially makes the oceans become more corrosive to these calcium carbonate minerals that are important for calcifying organisms, organisms that produce calcium carbonate shells, mollusks, crustaceans, and corals. So we've seen this picture from Richard. I'm just going to go through it again. There's the overall global ocean surface pH projections. You can see the different scenarios there going into the future. And again, just to highlight really the difference between the two emission scenarios, if we continue on a projection for the kind of 3 to 4 degree world by the end of the century, or if we stick to a 1.5 degree or 2 degree world, you see massive differences between this surface saturation, the surface corrosivity levels in the Arctic and the Southern Ocean. If we can stick to the lower emissions, then we save a lot of the ecosystem at the surface waters from experiencing those corrosive conditions. However, seasonally, we will still experience that. As Richard said, we're already locked into a commitment to a certain amount of acidification. But we've also heard about how species potentially move northwards. And we're expecting, I'm going to use an example from fisheries, where we've already got models that project that fisheries, according to warming scenarios, will be moving into the polar regions. However, a lot of these model projections don't yet take into account acidification in these issues. So one of the knowledge gaps we have is, what are these fisheries going to experience in terms of ocean acidification? And we have a PhD student who's been working on this issue, and she recently published a review that suggested that of the top 47 species landed in terms of recorded landings above 2,000 tons, only 21% of those species have been studied with respect to ocean acidification. So there's a huge knowledge gap in that respect. Of those 47 species, there were 41 studies with 60 experiments. Of those, 30% were on Atlantic cod. So you can see there's a massive discrepancy of where we're putting our energy in terms of understanding the species impacts. Again, of that, there was only 30% of those experiments were looking at ocean acidification alongside a second stressor. And this is really important when we think about the multi-stressors that these organisms are going to be facing in the future. They're not just experiencing acidification. We do need to understand that on its own, but we also need to understand how these species are going to be responding in this multi-stressor environment. And she summarized this in this figure. You can see the different species that have been studied with relation to ocean acidification. And she also showed how the different studies related to the different life stages. And most of the studies related to the early life stages, with very mixed results in some of the adult fish species or the fish, but more significant responses in some of the crustaceans. The red king crab, for example, or the northern prawn and the American lobster were more significantly impacted. She identified 3 knowledge gaps: the lack of studies on polar-specific species, or indeed, as we heard from Angus and previous speakers, the species that are going to be moving into these regions potentially, a lack of understanding of the multiple stressors, and a lack of knowledge of actually what these organisms are going to be experiencing. We have very sparse data for these polar regions, the Arctic especially, because it's incredibly difficult to go out and measure these parameters. So we're moving towards using new technologies. And this is some work that has just completed. It was a European Space Agency project called Ocean Soda, and it's looking at how we can use satellite-based observations to measure carbon dioxide and alkalinity and some of the associated products that allow us to look at changing pH. So we can use ships of opportunity, but we can also then use satellites, and satellite observations can be used to fill in the gaps by measuring related parameters such as temperature, salinity, and chlorophyll content. To speed up the process a little bit here, but you can see that once we have those in place, we can start to use those satellite and surface observations to combine them in a machine learning technique to generate global monthly maps that characterize the changing ocean chemistry. So you can see the different layers of information that are generated there to look at how the hydrogen ion concentration is changing, or the pH. You'll see now that this is a 30-year time period. So we go from 1985 through to present day. And you can see going from the green high pH conditions to the purple low pH conditions. And what you'll notice in these figures is that we do quite well in the global oceans, but we haven't really got much going on in the Arctic because we don't have the information there yet. So our PhD student has been looking at improving these satellite observations to really try and take that step forward to understanding the polar regions. And these satellites, alongside traditional in situ observations, can really help us to understand regional level variability and long-term trends. So this is examples from some of the time series stations we have around the world. We've got the Bermuda Atlantic time series in the top panel, the Hawaiian Ocean time series in the middle, and Erminger Sea time series in the bottom. And Erminger Sea is just to the south of Iceland. And the colored lines represent what the satellites and this product produces, whereas the gray dots and lines represent the real data that we have in these time series observations. And you can see generally they do pretty well. And that allows us to actually project back in time and look at the seasonal variability as well as the long-term trends. And we have confidence now in these satellite projections that they're actually capturing what we were experiencing in the real observations. So this is work that what we can do then is map changes in some of these products. It's starting to move up into the Arctic. So this is some of her latest work, looking at how we are actually able to start to look at the Atlantic inflow regions and also the outflow regions in the Arctic, and look at seasonal cycles. You can see the pulsing there as you go through seasons. And what we can do with this information is then look at biologically relevant oceanographic features. We can apply that to the biological knowledge. We can take this environmental data and put it into experiments to actually say what is it that these organisms are really experiencing through their life cycles. We can co-map on where the biogeography is of these species, the species that we're interested in, and actually look at how those changes are changing together. And also look at hotspots and areas of risk. So I'm going to finish there just by highlighting that there'll be a follow-up talk with Adrienne Sutton next, and she's going to be talking at some different technologies. But I think what we need to be looking at is how we can use these technologies to work together with stakeholders to really be minimizing the ocean acidification impacts. And we now have a good set of observational data. We're able to go out and collect that technology with the new technology, but we're also able to use these alternative remote sensing data to help to provide evidence that will stimulate us, hopefully, to reduce emissions, manage co-stressors, protect and increase habitat, but also invest in education, partnerships, and the science. So thank you very much.
Thank you,
Hello,
Helen.
fellow
And as
panelists.
she mentioned, we have Dr. Adrienne Sutton coming up next. This will actually be a remote presentation, but live. Is an oceanographer at NOAA's Pacific Marine Environmental Lab in the US. Her research focuses on advancing our understanding of the ocean carbon cycle and how it is changing over time by using autonomous ocean observing technologies.
Attendees of COP26. I'm sorry not to be there with you in person today, but I'm glad to join you virtually to talk about new observing technologies relevant to the polar oceans. 3 years ago, I had the opportunity to participate in an attempt to navigate an ocean robot completely around Antarctica for the first time. This footage from that mission shows why collecting surface ocean observations in the Southern Ocean is so challenging. The storms are massive, winds are strong and unrelenting, and the waves are huge. So the goal of this mission was to test the limits of autonomous observing in this remote and harsh environment. I was convinced the Southern Ocean would quickly swallow a little robot, and on an earlier test mission, it almost did, in an area where a wave as tall as an 8-story building was observed. But in the end, the risk was necessary to push the boundaries of observing in a region that plays an important role in our climate. The global ocean overall absorbs about a quarter of the carbon dioxide released into the atmosphere every year from burning of fossil fuels and land use change. Helen discussed how ocean uptake of CO2 results in ocean acidification impacts to marine life, but at the same time, the ocean uptake of CO2 has also provided humankind a significant service. Without the ocean absorbing this extra carbon released into the atmosphere, the globe's atmospheric temperature increase would be well beyond the 1.5 degrees warming threshold being talked about during COP26. And the Southern Ocean is an important part of this conversation because it plays an outsized role in our climate system. It covers only 30% of the globe's ocean surface, but it accounts for as much as 75% of excess global heat uptake and 40% of ocean carbon uptake. As these images show, processes in the Southern Ocean that impact this uptake are complicated, and they are highly variable in time and space. And it's challenging to fully understand and predict these processes because the Southern Ocean is unique in a lot of ways. It's the meeting point of ocean currents from other ocean basins and serves as a connector between the atmosphere and the deep ocean. As a result, there are some areas in the Southern Ocean where deep ocean water, naturally rich in carbon, comes to the surface, releasing CO2 to the atmosphere. And some areas where phytoplankton absorb carbon and sink, and where surface water is being drawn down into the deep ocean, sequestering CO2 from the atmosphere along with it. So the combination of this variable environment, the remoteness, and the harsh surface ocean conditions make the Southern Ocean very challenging to observe. This has led to uncertainties in our knowledge about ocean carbon uptake, and that in turn impacts our ability to track the entire global carbon system. Here's the 2021 assessment of the global carbon budget published just a couple days ago that shows the global balance of sources and sinks. You can imagine in the near future, the public and policymakers will want to understand how CO2 mitigation approaches are impacting this balance. But uncertainties in the ocean sink limit our ability to track the impact of these carbon mitigation efforts at the timescale that policymakers will be asking for that information. The uncertainties we have in the ocean sink also impact our ability to detect whether ocean uptake of CO2 is decreasing over time, which models predict may happen as the ocean becomes warmer, as its carbon chemistry changes, and as ocean circulation changes. But there is good news in that we now have observing technologies to help reduce that uncertainty. And that's where that ocean robot comes in. We also call them autonomous or uncrewed surface vehicles, and there are several different kinds out there used for a variety of purposes. The one that circumnavigated Antarctica in 2019 is called a sail drone. This uncrewed surface vehicle sailed for nearly 200 days, over 22,000 kilometers, collecting over 4,700 measurements of carbon dioxide in seawater and air just above and below the ocean surface. It survived freezing temperatures, 15-meter waves, winds equivalent to a Category 1 hurricane, and even a collision with an iceberg. I was involved because I'm interested in ocean observing technology that can fill persistent gaps in the ocean carbon observing network, and lack of wintertime measurements in the Southern Ocean represents one of those persistent gaps. During the portion of the mission where you see a lot of red on the figure in the right is where we observed strong outgassing of CO2 from the ocean to the atmosphere. This was while the surface vehicle was going through some parts of the Indian Ocean sector of the Southern Ocean where wintertime measurements of surface ocean CO2 had never been collected before. On average, across this entire region, the Southern Ocean is still an overall sink for atmospheric CO2, but it's this variability of CO2 uptake and outgassing in time and space that causes large uncertainty in our estimates. Now, if those videos triggered any seasickness, you may want to look away for this next one. Just this past September, a sail drone captured the first video at the sea surface inside a hurricane. At this point during the footage, the hurricane was rated a Category 4, meaning winds were blowing around 120 knots. This is another example of a time and place that you do not want to be on a ship, which is why hurricanes and other storms, like in the Southern Ocean, represent one of the persistent gaps in measurements of heat and carbon exchange between the ocean and atmosphere. So those types of uncrewed surface vehicles can excel at addressing our observing and knowledge gaps in processes that are happening at the air-sea interface. But another robotic instrument called biogeochemical Argo floats excel at connecting what we observe at the surface to the deep ocean. A biogeochemical float network was first deployed in the Southern Ocean in 2014, carrying sensors that measure ocean pH, oxygen, chlorophyll, and other ocean variables. They're deployed from a ship, drifting along with the deep ocean currents for 10 days when they then make a suite of measurements from 2,000 meters deep up to the surface and repeat that same 10-day cycle over and over again. They've already helped us better understand phytoplankton communities, how biological production in the surface ocean eventually leads to carbon storage in the deep ocean, how oxygen content is changing, and how circulation and other physical factors are linked to biology and biogeochemistry. Many of our observing challenges are most extreme in the polar oceans, and the tools that have been tested there can be used throughout the global observing system. We need to harness a diversity of these modern autonomous observing technologies in order to track the ocean's role in the climate system and the effect of climate on the ocean. At the same time, we need to maintain critical climate records that we've been gathering from ships and other platforms for decades. We need information about the ocean's surface from satellites, and we need state-of-the-art models. During COP26, you'll hear national commitments being made along these lines, including a commitment from NOAA to establish a global operational surface ocean CO2 network to track changes in the ocean sink over time. While most ocean observing is funded at that kind of national level, international coordination is critical to linking a diverse observing system funded by many nations together in a sustained fashion. So developing a sustained ocean CO2 network will also require the organizations you see in this image, including the G7 Future of the Seas and Oceans Initiative and the International Ocean Carbon Coordination Program. These types of initiatives leverage the existing science to societal knowledge framework that you see here, and along with the new technologies I talked about today, provide a great opportunity to truly build a sustained observing system that can provide the ocean information necessary to understand climate change.
Presentation. So we're gonna move to questions for a moment until Rolf is ready. He's not ready. Right. Okay. So any questions from the audience to start? And you can, I don't know which, I guess come here if you want to. Any questions? I mean, I'll ask a question. All right, I'll ask a question. So this is kind of a two-part question, and I would say any of you may answer it, but I may have to just call on one of you if you don't step up. So so it's a two-part question. What are the most important steps to bring together these multiple issues related to the polar ocean for policymakers and for policymaker decision making? And how are you yourself actually working to communicate this to policymakers? So, Richard, you were talking about the 2021 Cryosphere report, which is the first time I've actually been hearing about that. How effective do you think that's going to be? Do you want to start, and then we can kind of move down the line, and you all can mention something, and then we'll see. Hopefully, we'll be ready by then for our final talk.
Well, it's actually for the audience to answer that question, not me. But I think we have to do it at this multifaceted approach. I mean, these have been very different talks, but they're all working towards the same goal. And we are aware that the projections are not the strongest because of the lack of data that Helen said. And it's by populating the database, especially in the winter and in the uncomfortable seasons when you are sampling, that we can actually really affirm the decisions. But I'm not weakening what is written in this report, because when I'm saying we only have 14 years to go out to reach 450, which has been shown by many, many different approaches is a critical threshold, then this is a very powerful document without needing more data. But I think if we're moving into the deeper ocean, if we're moving into very local, regional policy advice, then we need to populate the data sets with the techniques that Adrian just shown then. So.
Think about your answer. So our final speaker is Dr. Rolf Rodwin, who is Executive Secretary of the Arctic Monitoring and Assessment Program, or AMAP. AMAP is organized as a working group to the Arctic Council, responsible for monitoring and assessing the state of the Arctic regions with respect to pollution and climate change issues and other impacts on ecosystems and human health.
Thank you so much, Libby, for the kind invitation and introduction and invitation for me to talk here. And sorry for the inconvenience regarding some technical issues in the very beginning here. So, as said, I'm the Executive Secretary of the Arctic Monitoring and Assessment Program, and I was invited here to kind of draw the multi-stressor landscape that some of the species in the Arctic ecosystems face or operates in. Oops. Yeah, okay. Seems like this file is a bit corrupted still, but hopefully it's fine. Anyhow, I was just going to start by referring to Richard's and Helen's introductions here just before me on Arctic Ocean acidification. We did a report in 2018, as you can see here, and actually 2 years ago at the COP, we presented a report. And one of the key findings, or the report kind of sums up some of the state regarding ocean acidification in the Arctic Ocean. It also focuses on 5 key studies from the area, from the western part of US on Alaska fisheries, Canadian shrimp fisheries, as well as Greenland, Norwegian cod stock, and Norwegian kelp and urchin population dynamics. However, one of the important parts, or one of the important recommendations from that report was to support further enhanced research, in particular on how acidification processes interact with other environmental stresses in the Arctic marine ecosystems. And that's where I'm going to take up the thread now. So just to put it a bit in perspective, like in the when we talk about acidification, for instance, you often see that as kind of, if you look, or if you view it in a kind of risk perspective, we often define, in this case, acidification as the hazard. And then the other factors influences the risk is the vulnerability and the human exposure. And when it comes to the vulnerability, a lot of the other factors I'm going to talk about are factors that influence the vulnerability of species. Species may have limitations of moving out of the area, or actually to adapt or even evolve in the long term due to some of these factors. So this spring we released these reports for Arctic Ministerial meeting, ranging from climate change to permanent organic pollutants, mercury, as well as human health and microplastics. And some of the key findings I'm going to refer to now are from these reports, and you can find them free for download at our webpage later on. So some of our key findings has already been referred to by Richard. Like when it comes to climate change, the overall take-home message is that the Arctic is getting warmer, and it's getting more warm. It's getting warmer more quickly than the rest of the globe. Actually, in our latest report, we have moved from saying twice, but to say 3 times the global average. So the picture you can see there shows the warming patterns from 1971 to 2019, and you can see the overall picture is a consistent warming, though there are some regional changes, also regional variations. And this is actually a more rapid warming than we reported before in our assessments. Likewise, as Jason Box presented the other day, the Arctic is getting wetter. The precipitation is increasing, but it's mainly taking place as increased rainfalls. As you can see of this slide, the more blue areas are where we found a significant increase in rain. So those dark blue areas, there's really strong increase in rainfall. And the special thing is that a lot of this rainfall is actually taking place in the winter months, so from October to May. So whereas earlier was snow, it's now rain in the Arctic. And it has some implications for other processes, as I will come back to soon. Sea ice has already been mentioned, but for the last 43 years, half of the sea ice volume is gone. It's a rapid decrease, and when it comes to the extent, it's about the same. And if I remember Walter correctly, it's about half the size of Western Europe has disappeared for the last 40 years. Likewise, if you're looking on land ice, or land fast ice, and in particular glaciers, there's been a rapid decrease in the mass balance of glaciers. In particular, when it comes to Greenland, as this green line, particularly when it comes to the Greenland ice sheet, as this green line shows, from 2001, it's been a negative mass balance, and about 5,000 gigatons of ice have disappeared. Yeah, and as I say, the Greenland ice loss contributes to about 50% of the Arctic total. There is change also taking place in the biota, in particular in the Arctic. So due to the increased opportunities for instance, harvesting, as the ice ages are shrinking, the fisheries are moving northwards. So trawlers are moving towards the poles as the ice is shrinking. Likewise, cod species, or fish species, in particular cod and Atlantic fish species, have been moving northwards. And they influence, of course, the endemic species up there. And particularly for some of those bottom-dwelling species, this has really some consequences. Because at some time, when you move northwards in the Arctic Ocean, you will face the ridge, and it drops down to 2,700 meters. And it's not so fun being a bottom-dwelling species at 2,700 meters below sea level. And of course, ocean acidification comes into this picture. The warming Arctic has also increased the human activities in the Arctic. Fish farming has become more common and move northwards, which brings with them some challenges to local species. The tourism has boomed in the Arctic. Also, when it comes to what we call nature-based tourism, like for instance whale safaris, which also implies disturbance on some of the species, and for some of them in vulnerable parts of their life cycles. And as well, there's been a development of industries like oil and gas industries or mineral resource industries in the Arctic, which also implies a local source for contaminants. So in total, the rapid change in cryosphere affects ecosystem throughout the Arctic, changing the productivity, seasonality, distributions, and interactions between species in all parts of the Arctic ecosystems. So, just to make the picture a bit worse, I feel a bit like Dr. Doom here I'm standing, but climate change also affects indirectly, like for instance on pathways for contaminants to be transported up to the Arctic, to be deposited in the Arctic, and how it's taken up by the food webs and accumulated in the food webs. For instance, like the sea ice enhances the exchange of gas between air and water, and also then the contaminants. So it can bring down some of the more volatile compounds into water, for instance, like persistent organic pollutants. Melting glaciers have been a deposition site for contaminants throughout the years since the Industrial Revolution. Thanks. And melting glaciers will then release or remobilize those contaminants. Likewise, melting permafrost or thawing permafrost releases mercury into rivers, and the river streams are increasing, so they washes out more contaminants into the sea, into the marine ecosystems. And we have observations of this taking place, both with regards to shifting season, permafrost degradation, altered food webs, changing climate patterns, and northward movements of subarctic species, as well as the diminishing cryospheres as well. However, I would say, and these are reported in our Climate and POPs report. However, I would say it's a very limited amount of studies. So yeah, I'll skip this slide. But in general, contaminants, they do have effects on species. We have shown for some of the species they do actually have effects on population level, like for instance for orcas, and also of course for humans living there. And as our report, as the CMIP 6 modeling in our latest reports confirms, the Arctic warming will continue, and it will be of a significant magnitude, up to 3.3 to 10 degrees above the average from 1985 to 2014 by the end of the century, of course, depending on emissions. So just to end with this slide, just to sum up, species living up in the Arctic faces a multi-stressor environment, both due to contaminants, hunting, disturbances, new invasive species, infectious diseases, habitat loss, and climate change. But in addition, climate change affects all of these other parameters. So climate has both a direct impact on the species, but also an impact by changing the kind of landscape, multi-stressor landscape the species is living in. And I guess due to time, we're just going to shortly say, when it comes to policies, it's very hard to have policies for multi-stressors because scales are independent. Some of them are on national level, some are international. You have to find the right level of introducing discussion, and you also need to find the right policy body. And I'm going to talk a bit more about that at 6 o'clock tonight. So I hope there's going to be an introduction to that talk. So thank you so much. Thanks.
Well, thank you to all of our speakers. We have, I think, about 8 minutes, 5 minutes, 2 minutes, 3 minutes. Okay, we have We have 3 minutes, which actually is perfect because my question to whoever of you all who wants to take it is, if you were caught in an elevator, if there were one here, with your COP delegate, and you could say one thing or maybe 2 things, this, not everything, because there's a lot of information that we do have, but if you could say 1 or 2 things, what would you say? It's a tough one. Maybe I'm going to let Helen try that one, and then we'll work our way down if we have a moment.
Too many tall people. That is a tough one. I'm going to go with the human touch. I've said this before back in 2013. My elevator pitch would be, I would like my children to learn about Arctic sea ice and glaciers and the ocean that we know about it in science and geography lessons and not in history lessons. Thank you.
Well, that's just as well, I think. I would just say we need to get back to basics and continue consistent monitoring of environments. And that is absolutely crucial, because understanding past change is absolutely critical to predicting the future.
I think I'd talk about those bowhead whales, and I'd make the point about their longevity, and I'd make the point about how little we still don't know about some forms of the functioning of the Arctic system, and by knowing more about them, we can make better decisions about iconic species like bowhead whales.
And Adrian, are you there? Do you want to try and answer as well?
I am here. I would say that the questions that we have to answer about the ocean are way out of scale with the commitments and the time and the funding that we have for ocean observing and research. So I would say we need to multiply that commitment by 10.
Right. And thank you for, I wish you were here, Adrian. You'll have to come to the next COP.
I will.
Would you like to try? We have one more. We have one more answer, and then we'll wrap it up.
I guess I would take the positive approach to multiple stresses and say it also gives you the opportunity to act, because even though you may not be able to do something with climate change today due to the inertia in the system, by doing remediation, or by doing legislations on contaminants or on other parts, on disturbance and so on, you are still helping the climate change issue. So by doing something, you actually have an effect, even though it's a complex environment.
I think the most important thing, and this is really strengthened in the report, is that 1.5 is not the best case scenario, it's the worst case scenario, and we should be heading for something much lower than that. And similar to Helen, I would also, as I have told my children, they should be able to tell their children of the football match and the barbecue on the Icelandic ice sheet that we had against the Germans, and we won. But it was Germany against the rest of the world, and I think we won. So.
I think the human touch is pretty important. So this event is over, and the next one will start in just shortly, 2:30, and I will also be moderating. So it will look like the same event, but it's not.